All right, folks. So this is section 2.3, example 5 from your notes. The question says, an n by n upper triangular matrix is one whose entries below the diagonal are 0. So when is such a matrix invertible? All right. To address such a question, I think the main goal here is just try to build intuition about what it means to be upper triangular. So I think the way to do this is to just build some examples. Let's do a 2 by 2 matrix to start. I have 1, 2, 3, 4. All right. So I have a 2 by 2 matrix. And so when is this upper triangular? So I need the entries below the diagonal to be 0. The diagonal entries, right, we have to remember are just the 1, 1, 2, 2 positions, right? So the things on the diagonal are here. So below this is just this one number. This must be a 0. Okay, and so the diagonal entries and the things above the diagonal entries can be whatever they want to be, 0 or not. Let's do a 3 by 3 case. I have my 3 by 3 case. Again, I look at my diagonal entries and say below those, I have to have zeros. So zeros for sure in these positions. And then the diagonal and above can be anything. Again, I'll mark by stars. Maybe just for good measure, a 4 by 4. But I think maybe now you have a sense of what this is going to look like. Four diagonal entries, below those are zeros, and then above those can be anything. Okay. So here are a bunch of n by n invertible matrices, sorry, not invertible, but upper triangular matrices. The question is, when are these invertible? Well, when I think about the invertible matrix theorem, which is the tool that feels really relevant here, right? I'm asking about when something's invertible. We have a million different things that are all equivalent. How do I determine which is the most relevant? Well, at this problem, I mean, I could ask, do I want to talk about linear independence? Do I want to talk about span? Do I want to talk about, finding a matrix C so that C times this is the identity? I mean, there's a lot of things it could be. But for me, when I look at this, I look at these pictures that I've drawn and immediately my mind goes to pivots, right? I see what look like pivots in all these pictures. So that's probably the relevant thing, right? So remember, A is invertible if and only if A has n pivots. So if you look at these pictures, when do these have n pivots? You might say, well, always, right? Because there's the diagonal entries, the stars, and those are pivots. But be very careful, right? Those stars could be any number, including 0, right? I mean, what if I make this a 0? That's possible. That's allowed in my definition, right? The definition just says things below it have to be 0. The stars could be 0 or anything else. And so that'd be problematic, right? If my diagonal entries is a 0, then I don't have n pivots, right? So at the very least, I am noticing that my diagonal entries, which are my pivot positions, need to be non-zero for them to actually be pivot positions. The stars above, I guess, can be anything. Those could be 0 or not. I don't care, as long as I have my n pivots. So I think I'm now convinced my answer must be such a matrix is invertible if and only if the diagonal entries are all non-zero. So then this A in particular, these upper triangular matrices are invertible if and only if its diagonal entries are all non-zero. Okay. Be very careful. This is not true for an arbitrary matrix, right? This is only true when I have these upper triangular matrices, right? Where I know that right? Everything below the diagonal is 0. Then if my diagonal entries are all non-zero, it's invertible. All right. Hopefully this makes sense. If you have questions, please let me know. All right.